quantitative assessment of earthquake-induced surface changes helps us measure what the ground actually did. We will build intuition for modern measurement tools and the key metrics used to analyze faults and landslides, and then see how multiple datasets are integrated into a single quantitative picture. First, how do we measure ground deformation at scale? We will build 3 quick diagrams: a radar interferogram concept, LiDAR differencing for volumetric change, and feature tracking from photogrammetry. Then finish with point displacements from GNSS. Radar interferometry compares 2 radar images taken before and after an earthquake. The result is a pattern of colored fringes, which are lines of equal displacement along the radar line of sight. Discontinuities across the fringes mark fault slip zones. Next, high-precision topography from LiDAR lets us compute volumetric change. Here is the idea in a cross-section: a slope before the earthquake and the same slope after, with erosion and deposition shaded. Subtracting digital elevation models gives delta V, the difference in volume. Photogrammetry tracks visual features to estimate displacement fields. We correlate recognizable pixels between pre- and post-images to measure shifts with sub-pixel precision. Global navigation satellite system stations record point displacements in 3 dimensions. Combining hundreds of vectors provides an independent check on satellite radar models and captures vertical and horizontal offsets with centimeter precision. Now, quantitative landslide analysis. A first tool is the frequency area distribution. On log-log axes, landslide counts typically follow a straight line, indicating a power law with slope near -2 to -3. Deviations at the small size and usually reflect mapping completeness limits, not physics. We can estimate total volume using an area to volume scaling. Combine the area distribution with V equals C times A to the gamma to get a total, and compare it to tectonic uplift volumes to close the mass balance. Where and when do landslides occur? We relate landslide density to shaking intensity with regression. Here is a logistic style curve versus MMI, with thresholds near 7 for onset and 9 for near saturation. We also often cite a PGA threshold around 0.15 to 0.2 G for widespread landsliding. Finally, global regressions predict total landslide counts from magnitude, shaking area, and relief. The form is log of n equals C1 plus C2 times moment magnitude plus C3 times log of shaking area plus C4 times relief. These capture trends such as more landslides in steeper, more strongly shaken regions. Next, fault displacement metrics. Scaling laws relate magnitude to rupture length and slip. On log scales, log of length equals alpha plus beta times magnitude. Typical strike slip examples. Magnitude 7.9 gives about 200 kilometers and an average slip near 5 meters. Slip distribution along the fault can be summarized by 2 key numbers: the maximum slip and the average slip. The ratio of maximum to average often lies between 1.5 and 2, and the coefficient of variation shows how uneven the slip was. For engineering, we use probabilistic fault displacement hazard analysis. That means estimating the probability that surface slip exceeds a target design value. A common conservative choice is the 84th percentile. The most robust picture comes from integration. Think of layers: deformation, landslide density, shaking intensity, and damage indicators, all overlapping to reveal the multi-hazard footprint of an earthquake. As examples, the 2015 Gorka earthquake combined geodesy, landslide inventories, and shaking records to map hardest-hit regions, and Kaikoura 2016 required multi-fault modeling plus tens of thousands of landslides and coastal uplift data. Putting numbers side by side in a geographic information system helps compare events and update models. Quantitative assessment is iterative. As higher resolution data arrive, inventories grow and numbers are refined. The goal is predictive capability. For a given scenario, estimate deformation, slips, and landslide impacts. By combining remote sensing, geodesy, statistics, and careful integration, we get closer to forecasting earthquake-driven geomorphic change.